In this presentation, we will be studying Chapter 10, and this one's Section 1. And in Chapter 10, we're looking at two populations. So that if we structure an experiment that we are comparing two processes or two populations, and we take random samples from each of those populations and then try to draw inferences if the two population means or the two population variances are different. So it will be a little different than what we had in Chapter 8 and 9, where we were comparing one population mean to a given number. We made that hypothesis mu naught as a given number. Now we'll be studying two populations in a comparison. So we see the outline here, and there's lots of sections. 10.3 is not here. We've already studied 10.3 in the non-parametric, so you've seen just a little bit of what two population samples look like. In this presentation, we'll be looking at section 10.1, which is going to be a difference in the means, and we're studying means when the variances of the distribution are known. And I know this is more of a textbook application because typically if you know the variance, you know the mean. But we will start out with this general format for a known variance first. Then we will move to section 10.4, which is for a paired t-test. This test is dependent, where our data is paired, and we're studying something similar to what you would see in drug studies, where we're comparing patients with a placebo and an actual drug, and we try to pair the two patients to be very similar. So that's section 10.4, and all the rest of these sections are independent. So the first 10.1 is independent, and I am going to combine 10.1 and 10.4 on your first homework assignment for this chapter. And then I will combine 10.2 and 10.5 for the next two homework assignments. So those two will go together. You need those two together you have to test the variances to be able to test the means there. So 2 and 5 will go together on our last homework of the semester, and 10.1 and 10.4 will be on this first homework. All right, let's get going. It's actually section 10.7, so this is the very end, and it's just a table to let you know what is in this chapter. And what we're looking at in this presentation is going to be section 10.1, and section 10.1 has known variances. All right, we are studying means. We're studying the difference in means from two normal distributions. They're independent distributions, and we're studying mu1 minus mu2. The first case is when the variances are known. The second case is when we have really large sample sizes and essentially known. We'll really be just studying this first one. This is all of the sections. The other one that I said would be in this homework will be the difference of two means when we are pairing them and getting a difference. So this is the paired analysis in 10.4. Now, when we are comparing two means, we first want to take two random samples, and those random samples will be from independent populations. All right, so in this section, 10.1, we're in independent. When we get to 10.4, we'll be in dependent. So that means that these two populations are separate. All right, they don't have one doesn't have any influence on the other. They're independent populations. The other thing that we need to know about these populations is that they are normally distributed. The samples come from the underlying distributions that are normal. And we many times write this as I, D. You'll see me write that in assumptions, which is identical, independent, normal. IID normal. Identically independent distributed normal. We are going to, in this section, be comparing the means from these independent populations, these two independent populations, and we're going to start out now in this section where we have the variances are known, so it's not a sample variance, we are given sigma. It's a typical something that you would have if you have a lot of past data and it's an historical standard deviation, and maybe you're just trying to compare, did the means change? Is something different in a small set of data when our variances have been, it's an historical variance. In this side, we will just look at our assumptions. We are going to have two different populations, and we're going to take samples from each of those. So our first sample will be X1, 1, 1, 2, 1, 3, 1, 4, 1, N. All right, so we'll have a sample from population 1. We'll also have a random sample from population 2. So you see each of these start with X2. X2 sub 1, X2 2, X2 3 to X2N. So we've got two separate populations, and we're going to be trying to understand the mean mu1 compared to the mean mu2. And those are independent populations. All right, so here we see X1, X2 are independent. We also must know that they are normally distributed. And that's what we'll write. This slide is what you will write in the assumptions section when you are writing an hypothesis test. You write your parameters are going to be mu1 and mu2, and our assumptions are going to be that they are independent random samples from a normal distribution. And this is what the expected value of those means are. If we take the X bar from each of these populations, the expected value of the difference, X bar 1 minus X bar 2, is going to be the expected value of X bar 1 minus the expected value of X bar 2, which should lead us to an unbiased decision of mu1 minus mu2. And then our variance of X bar 1 minus X bar 2, when we're looking at the variance here and we subtract, then we get the variance sigma 1 squared over the sample size N1 plus the variance of sigma 2 squared over N2. And you've seen that formula before in some things. This is our Z quantity now. We are going to be using the Z distribution. And we've used the Z quite a bit now. And our typical Z formula is that Z, let me go over here and write Z is equal X bar minus mu X bar over sigma X bar, which is sigma over square root of N. Well, now instead of having just one X bar, we've got two X bars here. So X bar 1 minus X bar 2 is the first value, and then we're going to subtract the mu of X bar, and we just saw mu of X bar is the same as mu 1 minus mu 2. So instead of having one value of X bar minus mu X bar, we now have two populations. And our standard error for that difference is the square root of the sigma squared over N1 plus sigma squared over N2. Right? And that is normally distributed with a mean of 0 and a standard deviation and variance of 1. So this is the formula we'll also be using to create our test statistics. So here you see that we'll be studying a null hypothesis, and in the null we have our equal sign, and we may write that as mu1 minus mu2 equals whatever delta we want to study. That is typically 0. If that is 0, if delta naught there, the delta between the two, is equal 0, then we could also write this as adding mu2 to both sides, and we get an h naught that is mu1 equal add mu2, and if this is 0 in delta, all right, then mu1 equal mu2. And that's the way we typically see this written. It could also be written where you subtract mu2 from both sides and you're left with 0. Now, you don't have to have the delta of a 0. You could be testing if the strength between two populations is at least 5 psi better. All right, you may be testing is the speed at least 40 miles per hour more. So if you have a number that you're trying to test the difference in, then that would be your new delta instead of just is there a difference of 0. All right, and that delta naught is what is going to go in this value that would be mu1 minus mu2. Your testing is that mu1 minus mu2 equal 0. That delta is mu1 minus mu2 hypothesized. All right. Now, we will be studying this for alternate hypotheses of not equal, of greater than, and of less than. And our p-values look the same as they have in the past. Once you calculate that z0, it is only one z0. It's not one for x2 and x2, x bar 1 and x bar 2. And our rejection criteria regions are identical to what they've had been in the past. None of that has changed. So let's look at an example here. A product developer is interested in reducing the drying time of a paint thinner. Well, just when you thought statistics could not get any more boring, now we're watching paint dry. You thought you were bored, stuck at home. It gets worse. No, it doesn't. Come on, guys. Two formulations of the paint are tested. Formulation 1 is a standard chemistry, and formulation 2 has a new drying ingredient. So this is the way that we use this frequently. This is probably the test that I ran the most in my life, was the comparison of a before and an after test. I'm trying to make an improvement to a process. I have my standard process and I have an improvement. And I want to see, did my improved process come out better than my old process? So this is just your standard everyday thing you do as a statistician. All right, now this next piece is not. From experience, it's known that the standard deviation, and it says known, for this drying time is 8 minutes. All right. So if it is a known sigma, that 8 is equal sigma. All right. And this inherent variability should be unaffected. I hope that you never, ever, ever in real life do what they're doing here. You always test to make sure that that standard deviation did not change, because it may be changing just as much as the mean is changing. But this is a textbook experiment, and we are going to set our sigma 1 standard deviation equal 8 and our sigma 2 standard deviation equal 8. All right. It says we're going to be collecting 10 specimens from formulation 1, so N1 is equal 10, and another 10 specimens from formulation 2. So N2 is also equal 10. Now those do not have to be the same size. One could be 10 and one could be 40. They don't have to be the same size. But we're going to now take this 20 specimens, 10 from each different drying technique. We've got 20 specimens, and we're going to paint them and dry them in random order. And that's really critical when we're running an experiment, that we try to pick a specimen and, maybe specimen 1 goes to 2, number 2 goes to 2, number 3 goes to 1, number 4 goes to 2, number 5 goes to 1, number 6 goes to 1. You randomly assign which one they go to so that you don't have something that you may not be expecting in the process to override your true results. All right. The 2 sample average drying times, we've got our average from our actual sample of 8 here now. And so we've got 2 X bar values. X bar 1 is equal 121 and X bar 2 is equal 112. And I always try to set up that kind of little table when I work through one of these, just so that I've got all my data out from the very beginning. And I also see that we're going to be testing at alpha equal 0.05. Now, what conclusions can the product developer draw about the effectiveness of the new ingredient? Well, we are hoping, all right, that this is going to reduce, the second one is going to reduce the drying time. And that's what he's trying to study in effectiveness. It's not written very clear here, but we're trying to study the reduction for reducing the mean drying time. So our parameter of interest is going to be mu1 and mu2. It is the difference in mean drying time okay, and you could write that as that difference being mu1 minus mu2, since it's a difference. Okay. The assumptions we saw on an earlier slide, they're independent for sure, independent, normally distributed, random samples, and the variances are known. I'll just let you know right now, this is really key, because we will study independent normally distributed means, and there will be 3 different test statistics based on what we know or do not know about the variance. So that piece is key for determining which test statistic you're going to be using. There will actually be 3 different ones. Now, our null and alternate hypothesis. We saw up here that we wanted this second formula to reduce the drying time. So we want mu2 to be less than mu1. That's what we're trying for. We want to reduce with the second formulation. Never, ever, ever start with the 2 first. If you do, it will change all the other formulas. So always write population 1 first. So when I go back to my alternate hypothesis, which is H1, right, I'm going to start with mu1. That's what I mean. I always start with the mu1. Now, in this, the way we have written this up here, mu2 less than mu1, then that means mu1 must be greater than mu2. mu1 greater than mu2. And our our null hypothesis is just going to be the opposite of that, that mu naught is mu1 again, and instead of greater than, it's going to be less than or equal. Always put the equal sign in the null. It always contains the equal, okay? And less than or equal mu2. Remember, we could write that, since they're not asking for a specific difference, we could write that mu1, subtract mu2 from both sides, so then it would be less than or equal mu2 minus mu2 is 0. So you could write this in either format. What this 0 here is going to tell you, though, is that 0 is delta naught in the test statistic formula. Now, I think we've got everything on this page that we need. We see that our variances, sigma 1 squared and sigma 2 squared, are both 8 squared, or 64, and we see n1, n2 are both equal 10. We have x bar 1 equal 121, x bar 2 equal 112, and for our reject region, we know that alpha is going to be 0.05. So I think that's all the data we need to work through this. They have given us our test statistic up at the top, and here's the one that you will have to know to pick, that it has a known variance. So in this formula, we've got sigmas, all right? It is a known variance, not an S there. If it is not known, then it is a calculated S, but we have a known sigma. With a known sigma, we're going to be using the Z distribution. Once it's not a known sigma, we'll have to go back to the T distribution. The other thing that we see in here is they have already written in the 0, which is the delta naught value, mu1 minus mu2. And then this formula comes from the page with all the test statistics on it. We will reject P naught if our p-value that we calculate, p-value, is less than our alpha value of 0.05, and this is a one-sided test, so we won't be doing anything in half here or doubling anything. And the other thing that we could look at is if our Z naught value that we calculate, and since this is going to be a greater than test, then it's Z naught greater than Z of alpha, which is 0.05. All right, so we're looking at Z naught greater than, and if we look up in our Z table, 0.05 out in the center of the table, and we read back to the left and up to the top, we get a value of 1.6, and it's halfway between the 4 and 5 columns, so we put 6.4 and a half. Right? That's our reject region, and I'm going to go down and draw that off, as we always do. Right. We're still working with a normal curve. Right. This is the Z distribution, so it's centered at 0. There should be 3 standard deviations on either side of that 0. 1, 2, and 3. And our Z alpha value is at 1.645. So the alpha, the entire 5%, all right, of the graph is shaded in this area, 0.05 or 5%, and that is the reject region. All right. Hope you're getting used to that by now. All right, now let's go back and do our calculations. Our calculations, we're looking at a Z naught equal, and go back to your formula up here. X bar 1 is 121 minus X bar 2 is 112, and then subtract the delta, which in this case is 0. Divide by, and then we want the standard error, so it's the square root of sigma 1 squared is 8 squared divided by n1 is 10 plus another 8 for sigma 2 squared over n2 is 10. And all those values are coming from right here. And those were just given to us as summary statistics. So if you try to run this in Minitab, you're going to run it with summary statistics. Right. When we calculate that out, 121 minus 112 is 9. And if we take the square root, all of this comes out to 12.8. Let's see, 8 squared is 64, divided by 10 is 6.4, and 6.4 is 12.8. Square root of 12.8 is 3.57770, I think. And when we divide there, we get 2.52. That is our Z naught value. So I'm going to come down to my graph and look at where is 2.5. So I'm going to, here's 1, 2.52. All right. That is my Z naught value, 2.52. That is obviously inside the reject region. So we are going to know that when we look at our conclusion, Z naught is greater than 1.645. So we see 2.52 is greater than 1.645. So we will reject HO. Now, just to make sure we also get our p-value in here, the p-value, we don't multiply by 2 because it's a one-sided test, and we're just going to look up in the normal table the value of 2.52. Now, we can look up the positive 2.52 and subtract it from 1, or we can look up the negative 2.52 and it'll give us the small area on the table. And when we look that up, we get a p-value of 0.0059. If you look up the positive value, you would have gotten 0.9941, which would have been everything that's not shaded over here. And the part that we want, that's the p-value, is everything in the tail beyond our Z naught value, and that part is the 0.0059. About 0.5% there. And 0.005 is definitely less than 0.05, so that counts and checks out as well, that we will reject HO. So now our conclusion, we can conclude that by adding this new drying ingredient, this new ingredient to the paint, that it does significantly reduce the drying time. There is sufficient evidence to conclude the drying time is less. All right. So I hope that one worked. You understand that problem. You will have a homework problem like that one. Then the next thing that we have with these is looking for the power of our test and our sample size. The power, finding the probability of power, and power we know is 1 minus beta. Okay, so the type 2 error is beta, and power is equal 1 minus beta, and that's what we're many times asked to calculate, is the power of the test. We set our type 1 error rate to be alpha, and that we set here at 0.05, and we would like to have a beta of about 0.1, maybe as big as 0.2, but not any bigger than that. So once we run the test, then we go through this beta calculation formula. And it looks very similar to what we've done before. The only difference here is you see your standard error has two sigmas in it, and we've got here a delta minus delta naught. What we would have had before was mu minus mu naught. Well, what goes in that mu naught space now is delta naught, a difference that we're willing to accept, okay? And so we will write this with a mu minus a mu naught, which is typically that delta naught is going to be 0, and we just say how big of a difference are we willing to accept. The one that we just worked on was the one-sided, so we would be calculating just the beta value if we were given a problem for this one, for the one-sided test versus the two-sided. On the two-sided, you have to do two calculations, right? And the big difference here again too is in the two-sided test, notice that we're using z of alpha, where on the two-sided we had z of alpha divided in half. One-sided just has z of alpha. The other thing that we try to calculate is our sample size. So for our two-sided sample, we're going to be looking at that delta again, okay, means the delta, and we know our delta naught in the problem we were working was 0, and we're using the formula for, we'll have a z, this is for two-sided, so it will have a z alpha divided in half, and the z of the beta that we are trying to get, typically beta is 0.1, power 0.9, and so we would be looking for the z of 0.1 there. This is the two-sided formula again, where the one below that is the one-sided formula, and notice the difference down here in the one-sided. The only difference is that we are using a z of alpha instead of a z of alpha divided in half. All right, so this again gives us our sample size formula. Let's work an example with the sample size. All right, so consider the situation that we were just working with the true drying times being as much as 10 minutes. All right, so instead of saying that we just want to know is one better than the other, here they're wanting to say we'd like to see the true difference in drying time to be at least 10 minutes. And want to detect that 10-minute difference with a probability of at least 0.9. Okay, I hope you remember what that 0.9 is called. That is power. Power is equal 0.9. That's not beta. Okay, beta is 1 minus 0.9 or 0.1. So we're going to need here from our problem that we worked before, they gave us a z alpha of 0.05, and in that problem z alpha was 1.645. We also need z beta, and that's z of 0.1, and if you look up 0.1 out in the center of the z table, you'll get 1.28 when you read back across. All right, so our sample size formula is written below. We notice that it has a z alpha here, not alpha divided in half, and we need to fill in these pieces for our formula. So n is equal z of alpha. Z of 0.05 is 1.645 plus z of beta. So we got two things, z of alpha and z of beta, and we wrote those down up here above, 1.645 and 1.28. And that's what we're plugging into this equation. We have to add those two together and square them. Then we're multiplying by what we knew sigma 1 to be, and in that problem, sigma 1 was equal 8, which was also equal sigma 2. So we're going to use that same thing again. Sigma 1 squared is 8 squared, or 64, plus 8 squared is 64 again, and we're dividing by the deltas. All right, in our null hypothesis, an alternate hypothesis before, our null was that mu1 minus mu2 is equal 0. So from that, we get our delta naught is equal 0 right here. The delta we're trying to determine a difference in, our true difference up here now, is 10 minutes. So delta is equal 10. I'm going to put that here. 10 minus 0 for delta naught squared. All right, so that's going to be 100. So if we work through all of this, we square add the 1.645 and 1.28, square it, and then multiply by the 128 there. We will get 1095.12, and we'll divide that by 10 squared is 100, which is going to be 10.9512. Right? Anytime you have a number, anything out here that's not 0 beyond the 10, then you always round up, okay, with a sample size. So 11 is the sample size. And what that means is I want 11 from each of the populations. N1 would be 11, and N2 would equal 11. So the beta must not have been quite as good as we wanted, because our sample sizes earlier were only 10. Now it says we need to go to at least 11, right, to get to be able to detect a difference of 10. Now let's look at the confidence interval for these. So we got a confidence interval on the difference of the means, and the confidence interval is again the exact same format that we have. Our first piece here is the estimate of the point estimate. The point estimate is x bar 1 minus x bar 2 instead of just a single x bar. We have everything that we add or subtract to that point estimate is the margin of error. Margin of error, which is what we also use in sample size. This is MOE, margin of error. All right. And inside of that margin of error, this piece was our standard error, which was our sigma 1 squared over n1 plus sigma 2 squared over n2 is our standard error. And this little piece right in here, the z value, is our critical value that we look up on the z table. So that formula is identical to what we've been working with before. We just have to put in, instead of a single mu, we have a difference between two population means, mu1 minus mu2 in the center. Since this is a two-sided test, notice that our critical value is for z alpha divided in half instead of just alpha. If you were looking for just a single confidence interval for a one-sided test, the greater than or the less than test, then you would only use half of this, and you would not divide the alpha in half. So we're going to work a problem that's got a confidence interval here, and we're working a two-sided problem, I see. The tensile strength test performed on two different gauges of aluminum spar used in manufacturing the wing of a commercial transport aircraft. Boy, I did that for a long time. From past experience with the spar manufacturing process and the testing procedure, the standard deviation of tensile strength are assumed to be known. In other words, we are using historical data. All right, we're using known standard deviation sigma. All right, so that's what allows us to use this formula. The data obtained are as follows. We have an N1 of 10, an X bar 1 of 87.6, and a sigma 1 of 1. So that information is for population 1. Then they give us the same thing, N2, X bar 2, and sigma 2 for population 2. All right, so we've got two different sets of data there. All right. If mu1 and mu2 denote the true mean, that's what we're trying to find, the true mean tensile strengths of these two grades of spars, we want to find a 90% confidence interval, not 95, 90% confidence interval on the difference in mean strength. So what's the difference between these two spar manufacturing processes? Mu1 minus mu2. And that mu1 minus mu2 is what is going to go in the center of this equation. And the equation got too wide here, I guess, to fit on the page. So we've got half of it on the left, half of it down here below for the right, and we've got mu1 minus mu2 in the middle. And we plug in, the x bar 1 is 87.6 and the x bar 2 is 74.5. So this piece is our point estimate, and that, if we subtract, is 13.1. That's the point estimate. 13.1. And we got the same thing right here, 13.1. Then we're going to add and subtract to that our critical value. So if we were looking for a 90% confidence interval, then that means alpha is equal 0.1. Alpha divided in half for a two-sided test is 0.5. 0.1 divided in half. And z of 0.05 is equal 1.645. So that gives us our critical value right here, z alpha divided in half. The next thing we want to plug in is our sigmas, and we see that the first one, the standard deviation of the first one is 1, and the standard deviation of the second one is 1.5. The sample size of the first one is 10, the second size is 12, so we've got a square, divide, add, square root, all of that, and we end up with all of this piece that is going to be added and subtracted, all of this piece here called our margin of error. That piece is 0.8820. So we're going to be taking 13.1, subtract 0.8820, and we end up with 12.22. We take 13.1 and we add 0.8820 and we get 13.98. That's the confidence interval around the difference. So I want to look at this for a second and just a little bit further. We got 12.22 and 13.98. That is the difference between the two, is between 12.22 and 13.98. Does that interval contain 0? All right. Is 0 our mu naught or delta naught equals 0? Is that inside that interval? No, it is not. All right. 0 is way back down here. So that is telling me this difference is a positive difference. We would reject the null, that there is no difference between the two. If there was no difference between the two, then one of these values would have to be negative, the other value would have to be positive. And that would tell us there's no difference because the confidence interval goes from a negative to a positive value. Here, both of these values are positive, positive 12 and positive 13. Both of those are way bigger than the 0 delta if we were doing a hypothesis test. So we know that there is definitely a difference in the two manufacturing processes for the spar. If you're asked to say how would you answer this with a confidence interval, for how would you answer hypothesis testing, is you're looking to see if mu naught, which is in this case now delta naught, the difference in the means, if it is inside of, if that 0 is inside of the confidence interval. Now let's look at the sample size formula when we're trying to calculate a sample size for calculating a confidence interval. And this sample size formula looks a little different than the one for the hypothesis test. In this one, we are picking for our sample size, what do we want our margin of error to be? All right. I'm going to put it at 0.75. On that last problem, our margin of error was 0.88 or almost 0.9. Let's say, and this is something you pick that you would like. Remember, the margin of error is on either side of the mu1 minus mu2. So our total error or total width of our confidence interval here would be 2 times 0.75 or 1.5. So I'm just going to select the margin of error 1.5, and that 0.75 is the error or E in this formula. Now in that last problem, we also had that we were using a 90% confidence interval. So alpha was 0.1, alpha divided in half was 0.05, and we need Z of 0.05, that is 1.645. The other things that we have in this formula is sigma, and in that problem, sigma 1 was equal 1, and sigma 2 was equal 1.5. That's off the last slide. So now let's plug all this in and see what sample size we would need to reduce the width of that confidence interval down to 1.5. Z alpha divided in half, we've got Z of 0.05 is 1.645 divided by the error, 1/2 the width of the confidence interval we want, and we're setting that at 0.75. We're going to divide and square that and then multiply by our variances. And so we've got 1 squared plus 1.5 squared. When we work that out, the 1.645 divided by 0.75 squared, that comes out to 4.81. And when we multiply that by 1 squared plus 1.5 squared, we get 3.25. Multiply, and the value comes out to 15.63. Now always remember to round up. We can't have a fixed 15.6 part, so we're going to round that up, and our sample size N1 equal N2, we will set them both at 16. On the last problem, we had an N of 10, N1 of 10, and an N2 of 12. When you work the sample size out like this, you'd set both of them at the same value of 16. So you've got to increase the sample size a little bit here from 10 and 12 up to 16 each to reduce the width of that confidence interval down to 1.5. The other thing just to look at is you can do a one-sided confidence interval. Your one-sided confidence interval is going to look just like the one that we had for two-sided, except for this value right here. All right, the alpha value is not divided in half. It is just Z alpha. And the upper bound is where you add something to the point estimate, and the lower bound is where you subtract something from the point estimate. So the lower you subtract. And that is all for working on the variances known slides. So the next one that I'm going to give you is going to be for the paired sides, and this will be your next homework.